Good morning, everybody. Okay. Good morning, Lonnie. Good morning. Okay, yay, that's it. Good morning. Okay. So did you finish watching all of those videos?
Yeah, they were really good.
Okay. Did you learn anything new?
I really liked the idea of living on a plane, like a membrane, a plane
Oh,
of a membrane of a higher
yeah,
dimension.
actually, I used the word mesh last time, but I got confused. That's not the right word. It's brain, right? Brain, which is short for, which is really coming from membrane. Yeah, good. We're living on a membrane. All right. Good morning, Leonie.
Morning.
So, what did you think of the videos? Did you like them?
Honestly, they I like them when they're more information dense and shorter. But
Okay.
yeah.
Yeah. So they do go on. They repeat. They're a little bit repetitive sometimes. Well, there was originally a 3-part series that was being shown, after a week, so people would forget things. But yeah,
Okay.
you're watching them all at once, so that's part of it. Yeah, I skip past certain parts myself. I see what you're saying. Yeah, definitely.
Okay, yeah.
Maybe we should just have one video, right? One
Yeah,
composite video with all the information in it. Yeah, so they didn't, yeah, then no one's done that yet. So I think that's a good project. Somebody down the line needs to make a better film that's a little bit more consolidated. But thank you for that. That's great. But did you learn anything new?
Yeah, I did learn a lot more than the book tells us, or like more
Yeah.
in
Well, the
depth.
book doesn't have it yet. It didn't exist yet. There was so much work, and even today, the string theory that we have is nothing like what you saw in the video. It's actually even gone further than that. So this is one of the things that we can pursue a little bit. We have a few more lectures to do, and actually we finally finished the book. This is the end of the book, but we want to talk about the concepts here. There's really some rich ideas that, whether string theory continues as it was in the film or develops some new ideas, there's still some fundamental problems or issues that have to be dealt with. And I think the video actually tries to show you some of these fundamental issues. Does a pretty good job. So yeah, let's just wait a couple minutes and get everybody here. I actually finally put up the paper for you guys so that you can read about the first gravitational waves, and we'll talk about that a little bit later. But I think that's one of the areas that we can move into is general relativity predicted gravitational waves, and finally 5 years ago we had the first detection. It wasn't actually announced until the spring of 2016, but the first gravitational waves were detected in September of 2015. I just realized I don't have to show you guys the paper anymore. I can say good morning, hi, hello. I'm a person and you're people. Okay, so yeah, we'll just wait a couple of minutes to get started. But anything that you remarked on that you learned watching the videos that you were kind of surprised by?
I was a little surprised at the idea that gravity would kind of, I guess, slip through to the higher dimension. Or
Yeah, well, that's something we're going to talk about. Is like, why is gravity so weak? This is a neat story to tell, right? Gravity is significantly weaker than any of the other forces. Yeah, so that's definitely very interesting. I agree. Okay, so let's see if anybody's actually on the stream. We got one person. Hello. Say hello. Okay, so we've got a couple of people here. All right, well, hey, there's Leona, yay. Okay, I've got my crew here, my normal crew. Good morning, good morning. So yeah, so this is, now that you've seen these videos, you have a little bit of a background, much more than anybody else does, by the way. That most of our population has no idea what string theory is about. So you have already entered a very select group of people who has some conception of how string theory might work, right? So what is the goal of theory?
To find a unification of all the forces of nature.
Okay, and so would you consider that currently string theory is successful at that?
No.
No, okay.
We haven't made any testable
Yeah, go
yet.
ahead.
So, because despite everything everyone seems to know about it, we can't make any claim that we can use stuff that we specifically got from string theory. We can't predict anything from it quite yet.
Okay. All right. Well, that's fine. But actually, but what about the, there is this kind of beauty in it that you and I might appreciate. What are the, what are some of the positive elements that have already been done in string theory? Actually, the standard model kind of got them started, right? A lot of the standard, we like the standard model because it explains all of the particles in the universe, right? Everything. Well, almost everything, maybe, right? Doesn't explain gravity. So anything that might be associated with gravity would not be explainable with the standard model. But the standard model does a great job of unifying the concept of forces and particles, right, in one thing. So you have these bosons, these gauge bosons, which communicate the forces. So in this video, the set of videos, they talk about that, and we've already talked about it somewhat. But can you guys tell me what is the force carrier for the electromagnetic force? Do you remember that?
Is that one the gluon?
No, the electromagnetic force.
Photons.
The photon. Okay, the photon, right? A photon, a virtual photon, is exchanged between particles that are feeling the electromagnetic force. So positives repel positives. You can imagine a virtual photon bouncing between them. It's a little bit trickier to explain attraction, but they do it. And I'm not a theoretical particle physicist, but I tell you that they really convincingly believe that this particle can bounce back and forth. It doesn't actually, you can't see it, but it's a virtual particle, but it's a photon. A photon, the photon creature, the photon electromagnetic wave idea, when you use it, can communicate the electromagnetic force between two particles. It's a strong force, right? And is it the strongest force that we know about?
No.
Is there another force that's stronger than the electromagnetic force?
Isn't it the strong nuclear force?
Okay, how about that, right? These protons repel each other, don't want to be together, and yet the strong nuclear force forces them to be together. That's amazing, right? And so this is a stronger force, but of course a much, much smaller range. And what are what are the particles called that carry the strong nuclear force?
Gluon?
The gluons, right? And that's a little joke, but anyways, it's kind of, I think it's kind of funny, but it helps you remember that the gluons keep the nucleus together. They are mediating the interactions between the nucleons, which is either a proton or a neutron, within the nucleus. So the strong nuclear force we attribute to holding together the nucleus, but also to hold together the individual particles, which are the nucleons, right? And they are, in fact, you guys learned this already, they are a combination of three quarks bound together. So the strong nuclear force binds them together. And somehow these gluons are bouncing around between the gluons and keeping them together. And they're bouncing around between the nucleons to keep them together. Yeah, again, it's an attractive force, right? This is it's not a repulsive force. That's an interesting idea, as far as I know. I don't know that. Maybe I'm wrong, but I think it's just an attractive force. And then there's the last one that we know about, which is also a very powerful, very strong force. It's not called strong, it's called the weak nuclear force. Does anybody remember the name of the carrier particles for the weak nuclear force? Again, it's just remembering, but if you've looked at the standard model picture, you might remember the names of them. Anybody remember the names?
Bosons?
Well, that's a generic term for them. Photons are bosons too.
Oh, right.
Gluons are also, they're called gauge bosons, yeah. What is the name for the carrier particle for the weak nuclear force? Okay, so I'm just going to go ahead and look it up for you guys so that you can review. And so, but if you look up standard model, okay, here's standard model. There's a picture of the standard model. Can you guys all see the picture? Okay, so here are the gauge bosons. Okay, so the gluon is the mediator for the strong nuclear force. The photon is the electromagnetic force mediator. And the Z and the W. Now, this one is funny. I don't know why there's two. I don't get that, but there are. And there are actually, so there's two different force carriers for the weak nuclear force. Okay, so you should know what's associated with what. And then this one is a new one, right? The Higgs boson, and we've talked a little bit about that. That would be, that's the interaction with the Higgs field, right? Which is somehow permeates the entire universe. So there's all of these things that we have to assume are there, right? In order for this thing to work. First of all, there is a Higgs field because we've detected it now. And the Higgs field, the reason this was so important, remember, was not because of the boson itself, which is the force carrier for the Higgs field, but the fact that this exists means that the Higgs field exists, and presumably is the reason why particles have mass, right? The stronger the interaction with the Higgs field, the more mass a particle will have. So now we have, wow, this is an extension that we did not bring in before, but it's actually mentioned in the videos, the concept of the graviton, right? The graviton would be a carrier for the gravitational field. It does not exist in the standard model, right? This is a theoretical idea. But one of the things that I find really exciting is in the video, you saw some of the work by string theorists that actually indicates perhaps, you know, a graviton. Do you guys remember who was the theoretical physicist who may have discovered the graviton within string theory? I forgot to write his name down. I don't, you know, kind of like, I'm not an expert on this, but I was watching the videos too. Anybody? Okay, so in the, yeah, this was in the third one. One of the researchers was playing around with the string theory and then said, well, maybe this is explaining gravity, right? And they looked at their assumptions and realized that the strings had to be incredibly tiny, right? Much, much smaller even than a single quark, right? Much, much smaller, down to the Planck scale. What was the guy's name? I forgot his name. Anyways, once he realized that, he had this massless particle that behaved, that seemed to communicate gravity, right? So he had perhaps.
Susskind.
What was his name?
Leonard Susskind.
Well, Leonard Susskind was one of the guys, but that's not the guy I'm thinking of. There was another fellow. Can't remember his name. I could probably find his name
Sorry.
real quick. Yeah, there were so many names. Anyways, yeah, Leonard Suskind's a big guy, actually. He's pretty important. But someone else I'm thinking of. But anyways, the graviton may have been found in string theory, right? We have no graviton.
Schwarz.
What was that?
John Schwarz. In
Schwarz,
1970.
that's it, Schwarz, that's it, Schwarz, that's his name, John Schwarz. John Schwarz and his team, basically showed mathematically that this massless particle could be the mediator for the gravitational force. And so that's kind of an interesting thing. Well, again, it hasn't been shown to be real, but what it does is string theory has this richness to it that may be able to express everything, right? Everything, including gravity. And if that's the case, then, the hope is that it's just a matter of time before they come up with a testable prediction, right? And presumably, what do we mean by testable prediction? What is something that is testable? Are the strings going to be detectable?
Sounds like there wouldn't be because they're just so small.
Okay. So, but maybe, technology will just progress. Leona, you were going to say something. Go ahead if you want to say something.
Oh, I was gonna ask if you were asking what it means for something to be testable. I didn't know what you were asking.
That's an interesting question. What does it mean to be testable? Yeah, sure. Let me ask that question. What does it mean to be testable?
Basically, you can prove something wrong, or you can set up some test where you can observe or detect something.
An experiment of some
Yeah.
kind, right? Okay, so testable. Yeah, I think that's what I meant, but yes, that's okay. Thank you for the question, though. That's great.
Yeah.
So testable really means there's some kind of an experiment that could be performed. So direct detection. So you have some idea, how big are the strings that we're talking about? Anybody remember the dimensions? They're a little bit, maybe they're a little sloppy in the movie. They don't tell you dimensions. Leone, do you remember the dimensions?
I know that they're smaller than quarks and they are on the 11th dimension, but I don't know if
Okay.
that answers the question.
Not exactly, but that's good though. That's actually important. So the strings, actually you said something that's kind of interesting. You said they're on the 11th dimension. What does that mean?
That there's a lot of spatial dimensions that we can't see, but
Okay.
mathematically they've figured it out.
Are they in our dimension as well, or no?
Yeah, we just can't see it.
Okay. So, okay, I think there's maybe something that you want to clarify a little bit. So the idea was that there are 11 dimensions, right? This is actually one of the questions you're going to get on your final, right? How many dimensions do string theories have, right? And that's kind of crazy, 11 dimensions. But I guess my question was, what is the size? What's the scale? Does anybody know the scale? So the strings are on the order of the Planck length, right? And so these meshes, not mesh, it's not mesh, it's the wrong word. The membranes, that was the word I meant to. There's another concept that I think is related. Now that's probably where I got the mesh, but a mesh is a network and the brain is actually the name that they give. Sorry about that, I just got confused. So membrane, a surface, a topology, and it may be an 11-dimensional surface, but it's a surface, a connection of string. Okay, so we still haven't answered the question, how big are strings? And the answer that I would say is on the order of the Planck length, right? So what's the Planck length? Which we've talked about. What is it? 10 to the negative, we should write that down. What's the Planck length? So the strings we think are so small, they're like the Planck length, right? They are the fundamental units of space-time, right? Planck length. And so the Planck length is some number, but the order of magnitude is what I'm looking for here. 10 to the minus 35th meters. Okay. So now you might say to yourself, maybe one day we'll have the technology to see this, right? Just a matter of time. And actually, if you look at technology progressing, we are getting better and better. Listen, I mean, this is just so crazy, but when I was your age, when I was a student, you know, I was told that we would never be able to see atoms. And we not only routinely see atoms, we see things much smaller than atoms, actually, or beginning to, right? Actually, if I asked you the size of an electron, what's the size of an electron, right? So the answer is, I don't know. I don't know. What we have are these boundaries, right? We have boundaries. We know that it's less than something, right? But we actually don't know the size of an electron currently. Okay, so just think about that for a moment. Electrons are definitely not the smallest thing in the universe. They are much, much smaller than the neutrons and the protons. But the answer to the question, how big are they, is not something that I can answer. I mean, I imagine I can look up the latest experiment. Let's, you know, with the Wolfram Alpha right now. Let me ask Wolfram Alpha. I'm just kind of curious. You guys want to see this too? You guys can watch in real time as I screw things up. Let's just see this. Okay, I love it. Let's just do it. Okay, size of an electron. Size of an electron. Oh, well, we've got an answer. Okay, you want to write that down? Sure, let's write it down. According to the Wolfram Alpha, I'm wrong. Okay, 2.8 times 10 to the, what's femtometer? Does anybody know femto? Let's write femtometers. Okay, 2.8 femtometers, which is kind of cool. I guess you could just click, oh, it tells you right here, -15, okay? 10 to the -15 meters, femtometer, okay? So I don't think that's right, to be honest. I don't think that's right. I think that is an upper bound, perhaps. I just don't believe it. Oh, classical, I don't know, let's see. No, there's something wrong here. This is not right. We don't know the size of an electron. Come on, don't give me that. There's just no. I just don't believe it. Characteristics, observation. Okay, here we go. Observation of electrons. I don't know, size. Okay, well, I just don't believe that. That's some classic, I don't know what that is. Anyways, okay, so I haven't proven anything yet, but this, if anything, would be an upper bound or something. I don't know what this is. This is not right. It can't be right. We don't know the size. I don't know. I can't be that far off. Okay, I'm just going to tell you that I'm missing some information. I don't know. I'm not an expert at this, but I don't think we really know the size of an electron. It's so small that we don't have technology to see this. Well, here is a number that somebody has written down, and I thought that we had done even a little bit better than femtometer resolution. But anyways, this is pretty close to the limits of human endeavors right now, right? This is the smallest distance that can be measured. So if you compare and contrast, what is the size of an atom, the typical size of an atom? And the answer is about 10 to the -10 meters. Okay, that's an atom. So we are routinely 5 orders of magnitude better than the size of an atom. Not routinely, this is obviously pretty hard to do. But the point is that the people who told me when I was a kid that we will never see atoms were completely wrong, right? And in my life, we have gone from not seeing atoms to being able to see even smaller than atoms, right? The size of a proton is much better known. A proton or neutron, the order of magnitude is about 10 to the -15 meters. Okay, so this this is the femtometer. This is what I thought we would know. Okay, so here I am using the femtometer again. So actually, you know what? Now that I say that, I feel like I just want to check. Can I just check real quick? The size of a proton. Size of a proton. 0.87 times 10 to the minus 15. Okay. Because protons are not fundamental particles. Okay, this is according to Wikipedia, which I like very much. You should not just rely on it, but look at the papers that are listed and try to understand. So the size, the mass, the size, let's see size, oh here, radius. Here we go. Okay, here we go, this is it. In 2 different studies using different techniques, they have found the radius of the proton to be 0.833 femtometers plus or minus 0.01. Okay, so this is science, right? This is science right here. Somebody has actually measured the size of a proton, and I see here their uncertainty in the size. This is when I know I'm reading scientific information, okay? Because it doesn't tell you that this is the size, it says within this range, right? That's real information. So this is pretty much the resolution that we have right now in human technology. So femtometer. So how does that compare to the Planck length? And you see that we are 20 orders of magnitude. Now, as much as I'm an optimist, I have to be realistic as well. And there is no way that in our life, we're gonna get to that scale. It's not gonna happen. So if you are a theorist working on this theory and you say, well, my life is, I'm a scientist, right? But here I am working on string theory, and I know I can never detect the strings, then what am I doing, right? What am I doing? And obviously, it's not going to be to see the strings, right? We will not see strings. I love to say this because I could be wrong, and I hope I'm wrong. Strings in our lifetime, right? So then what will we see? It doesn't mean you can't predict something else though, right? We can still predict higher order quantities, right? So we can actually start thinking about not necessarily the individual strings, but how they group together, and maybe something a higher order version, right? So something like the particles that we're talking about, the electron or the proton. How do you make one? How do you make one from strings? And then how do you test that? So the testable theory will not be the individual strings. That's my prediction. Okay, I could be wrong, but I just don't believe that we're going to get 20 orders of magnitude. It's not going to be able to be something that we can do. Maybe, a couple hundred human generations. I don't know. But I do believe that eventually, technology will progress. And I do believe that the string theorists are going to come up with something that will be testable, right? There will be something that they can do to predict a particle. And when they do that, and they predict the particle energy or the mass, right? Then that is real, right? That becomes a legitimate science at that point. So it's not ever, I think this is kind of an important thing to understand. It's not that string theory is probably going to be able to detect strings. We probably will never do that. Well, not in our life, it's not going to happen. But we can still imagine that there's going to be a prediction that they can make. Okay, so they've been really successful at building this mathematics. And actually, I did want to talk a little bit about the quandary, right? One of the things that I've asked you, or I will be asking you about if I haven't asked you already, is that string theory seemed to be having problems that different people were coming up with different theories. So do you remember how many different string theories they talked about that seemed to be valid, that seemed to be coherent? How many different string theories there were for a little while?
5.
There were 5, right? So there's 5 different string theories, and they're all supposed to represent reality. So that seems to be a problem, right? And, you know, so what do you do, right? And so that's a problem, right? If you can't have 5 different theories of reality, they're supposed to be the same. And so this was a huge issue in string theory. I mean, there was actually this big feeling like maybe we're wrong, right? If you come up with 5 different versions of string theory, you know, then how could there be a single theory of everything? And that seems to be a problem. So what was the resolution? How was it resolved? How was this resolved? Okay, anybody remember?
It was from Ed Witten.
Ed Witten, okay. So he was actually, okay, Ed Witten, tell me about Ed Witten. What do you remember?
They described him as like a potential Einstein successor with how well he was able to conceptualize all these ideas. He took a look at the 5 theories and he wanted to see if he could get rid of any of them for some reason. And it seemed like on his attempts to do that, he realized that they all ended up saying the same thing. It was just like different ways of telling the same math, the same story of what's going on.
Mm-hmm.
So they ended up saying that all these 5 different theories are just different reflections of seeing the same theory, and it's already unified.
Okay, so that was a pretty profound moment, right? So even though there were 5 different theories, Ed Witten, so do you remember the year of that conference? This is a big deal because 1995.
UCSC.
Was it UCSB or USC?
University of Southern California, USC.
Yeah, USC, right, at USC. So there was a USC conference, and everybody was, you know, excited about string theory, and they were doing all these talks, and there were all these different talks. And then Ed Witten came, and in this one talk, changed everything, right? Because everybody was kind of saying, oh, 5 different theories, you know, which one's right? Which one should I work on? And you know, how are we going to integrate? And then he comes along and shows that these 5 different theories were just different sides of the same, you know, same creature, right? There were just 5 different versions of you know, 5 different paths that people were looking at, 5 different sides of the same. How do I do 5 here? I got to come up with some different. We'll make this one jaggedy. You know, there's 5 different views of the same cohesive picture, and I need my last one. What's my last one going to be? I don't know. Wow. Okay, so we have these 5 different points of view, but ultimately they are in fact unified. Well, so that's pretty amazing. But one of the requirements, what are the requirements in order to unify them? What did he require? Do you remember? Or did they talk about it? I don't know. I think they did. So one of the requirements is 11 dimensions. So 11 dimensions are required, and if you have these 11 dimensions, all of these theories are actually versions of the same theory. And so that was remarkable, because now instead of fighting each other, everybody's work was fitting together. This was super exciting. And actually, you want to understand that this was a depressing time, and suddenly this guy's talk and unifying the 5 different theories gave everybody a new burst of energy. And now they were suddenly on the right track again, right? Everybody was kind of like reinvigorated. So it was a really profound impact on the community. And so when you talk to people who work in this field, you understand it's a little bit hopeless sometimes. You're kind of like, what am I, you know, when are we going to ever get anything? But I have to say that, you know, we've seen a number of avenues come to fruition, right? One of them recently is the concept of gravitational wave. And so, you know, one of the encouraging things is that it took a long time before gravitational waves were observed. It was like 25 years really from the first, you know, trials to build a gravitational observatory to 2015 when they first observed gravitational waves. This is, you know, it's a big venture. It's very difficult. And so the string theory shouldn't, you know, string theory shouldn't be disappointed that it's taking a while, because it really is a difficult task, a really incredibly difficult task. Okay, so you've got these 11 dimensions, and where are they, right? So where are these 11 dimensions? So this is one of the issues that you want to be able to confront. How could it be that we live in a universe of 11 dimensions? Where are they? Anybody?
Aren't they on a really small scale?
Yeah, really small scale. Okay, how do you do that though?
How do you do what?
How do you make it a really small scale? What does that mean even?
I don't know how to answer that.
Okay. So actually, let me give you a physical model to work with to maybe try to show you something, okay? So I'm gonna go ahead and do something like I would have done in class with you. I want you to imagine that, you know, there's 11 dimensions, but I certainly I don't perceive 11. How many do I perceive? How many do you perceive? Anybody?
3 plus, well, I guess you can kind of see time, but
Yeah, use time. That's okay. Yeah, use time. Time has to be in there. String theory has to talk about time as well. So then that's a total of
4.
Okay, 4. So we're up to 4. We got 7 more to go, right? But the thing that's interesting is, you know, for example, I hold up the sheet of paper, right? And actually, let me go ahead and draw. This sheet of paper is presumably it's got 2 dimensions, right? It's got 2 dimensions. Now I see the 2 dimensions, but actually I can really quickly show you something interesting. Even though this is 2-dimensional, is this still 2-dimensional? And is this still 2-dimensional, right? And I haven't seemed to do anything to the paper, but it is different, isn't it? Right? This is actually, this could be considered a dimension, right? This rotational dimension. It doesn't seem to do much, right? But you can perceive a difference when you look at it, right? So some of these dimensions may be like that, right? Things that you and I cannot ordinarily see. Imagine if I shrink down to the size of a proton, but I start rotating it, right? I can't see the rotation of the proton, but it may be a real dimension that the proton has, that rotational dimension. So some of these dimensions may just be not obvious to us, but they're there. We just can't see them. Okay, but anyway, take this piece of paper, and what I want to do is I want to reduce the number of dimensions of this paper. So what I'm going to do is I'm going to coil the paper in a dimension. Okay, so if I coil that, so that I'm not going to do it. This is a difficult thing to do, but you know, I'll do my best right here. I should have made it a little bit lower to the bottom, but okay. I think I'll just tuck it in here so you guys can still see it. All right, so I'm coiling this dimension up, and then I'm going to show you something, right? That's the goal. Okay, so I've curled up this paper, and can you guys still see the one axis, right? So I haven't done it perfectly. You'd have to coil it even tighter than this. But the idea is if I could coil one of my dimensions around, it would still be there. It would still be within the paper. The paper is still the same paper, but I can't see 2 dimensions. I only see 1 now, right? So I've effectively reduced the number of dimensions. And then you could do it again, right? So I actually can coil it again, and you can see that I can create something that has effectively now how many dimensions? If I reduce 2 dimensions down to 1, and then I'm reducing one dimension down to. So it's hard to do, but you know, there's a point. It's supposed to be a point right there. This is the original origin right here. That's the original origin. And so if I did this really well, you would be able to see, I mean, obviously there's a limit because paper, when you fold it, it gets harder and harder to fold. But as you roll it up, you could imagine if these are infinitesimal, you know, if these are 0 thickness, and then you roll them up, then you coil them up, you can actually see a single point here. But really inside of that single point are 2 other dimensions that I just coiled up. And it could be even more like that, right? So these coiled dimensions don't seem to have much physical size, right? And so this is the explanation, right? That so that many or most of the dimensions are not visible to us, but exist in the somehow coiled up way, right? So I don't know if that's right, but I do know that that's what they think, right? So that there has to be 11 dimensions. So these 11-dimensional strings create networks. Anybody want to tell me about the different particles? Do you remember reading or hearing about, sorry, not reading, hearing about different particles? How do different particles exist? How do you have different kinds of particles? I thought this was kind of an important idea, and we kind of touched upon it when we talked about strings, just ordinary strings last time.
Like, are you asking about the theoretical particles that are introduced with string theory, or?
I just mean, how do the strings produce different particles, right? If they're the same strings, how could the same little strings, right? I have a little string. How could the same string produce different kinds of particles? How could that be? Why don't we just get a whole bunch of the same kind of particles?
Because a string could vibrate in an almost uncountable different number of ways.
Exactly, right? And so this is different frequencies, and you might even think it's similar to the concept that we use of the harmonics, right? These are like harmonics. And then there was something else, right? So there's different frequencies of a single string, but then there's something else as well. What else can happen? We've kind of already talked about this a little bit too. When you look at the string, how does it wiggle, right? And it wiggles, you know, all these ways. But there's another important concept, right? Maybe some of the strings are not actually wiggling freely, right? What's another way that they could be existing?
Close-ended.
As closed. Yeah, they end up as loops, right? And that's dramatically different. So we have 2 basic architectures. We have strings that are free and strings that are looped. But in fact, that's not really right either, because most of the time these strings are not just floating on their own, right? They're connected. They're connected to what? So where are the strings connected? What are they connected to?
They're connected on the endpoints.
They could be connected on the endpoint, but to what? What's that called? Right? We mentioned it already. Right?
Oh, to the fabric of space-time.
To space-time, right? To the brain, right? To the brain, right? So you can imagine that these strings are, you know, wiggling off of the brain and connected in only one spot, or they can be connected in 2 spots and wiggling to, you know, to different ways. So I didn't draw the wiggle, but there's a wiggle here. Or they can be loops, right? So these are pretty much the 3 possible variations in how an individual string could exist, right? They could be connected in one place or 2 places, or just connected to each other and not connected at all. And so this is why they are explaining what happens as a result of this. Well, remember our force carriers, right? The force carriers, force carriers. And one more time, let's just review, right? For the EM force, what's the force carrier? One more time, the photon, okay? For the strong nuclear force, right? What's the carrier?
Gluon.
The gluon, right? And for the weak nuclear force, the W and the Z, right? There's two. Actually, I think there's, I don't, just call it WZ, okay? And now for gravity, what's the force carrier?
Graviton.
This is what we call the graviton, right? We hope that it exists. It would be awesome. If string theory predicts the graviton and then tells us a way to measure it, that would be amazing, right? That would mean that we no longer have two separate theories. We have a unified theory. That would be amazing. Okay, so what about these forces, right? Are they the same strength?
No.
No, right? So they connect in different ways to the brain, right? And so one of which one is not like the others, right? So which one of these forces is not like the others? One of these forces is not the same. Did you guys watch Sesame Street when you were a kid? Anybody?
I did, but I don't remember much of it.
Oh, you don't remember? Okay, so they would put like these shapes right here, and they'd go, one of these shapes is not like the others. One of these shapes is not the same, right? You go, and that's part of your, like, children learning how to distinguish things that are the same from different, right? How do you sort, right? How do you sort things? And this is a skill that humans need to have sometimes, I guess. But one of these forces is not like the others. Which one is not like the others? Which one is distinct and different?
Gravity.
The gravity, right? The graviton is distinctly different. So these three have already been shown to be united, right? And it is called, what is it called? The electro weak force. They are united, right? So, but not in ordinary conditions. Can these be shown to be the same in our current state of the universe? Does anybody remember why these are combined? When do you get to combine these? When do they behave as a single force? When do they behave as the same force? The forces are united when? In the very early universe, right? The conditions were incredibly hot and dense and not like we have today. So this electroweak force, what they showed in the standard model is in the conditions of the early universe, there was no difference between these forces. They were unified and they are the electroweak force. But gravity is not there, right? Somehow the graviton is missing. So these three have already been shown to be united somehow in the very early universe, but not gravity. And so the graviton and gravity is distinctly different. So what is the reason that they give? Why is gravity so weak, right? Why is gravity so weak? There's an explanation, right? This is a pretty cool thing though, right? Up until now, I would have said to you, we don't know. But what was the explanation given by the string theorists in the video that you watched?
It seems like it almost loses its energy to escaping from outside of the boundaries we can perceive of our universe.
But do you remember
So,
why? Why is it? Why is it so weak? Is it strongly connected to the brain or not?
no, it's its own close-ended loop, so it's not binding to the rest of the strings.
Exactly. So when you think about a brain, which is meant to be, an 11-dimensional, brain, and you ask yourself, how does gravity interact? The answer is it's weakly interacting. It doesn't interact. And why? Well, because it's closed, what happens? It can actually go through without stopping, right? It doesn't interact strongly with the field. And so this is the idea. So this is meant to be 11 dimensions. The difference between the ones that connect to the brain is that when they're strongly connected, the force is strong, right? When they're weakly connected, the force is weak. And what happens is that that force kind of, instead of being concentrated in this connectivity here, is dissipated by spreading in all of those different dimensions, right? So gravity is so weak because it is not strongly interacting with the brain that we are existing within, right? The place where we live. And it seems to be able to easily go from one place to another, right? So this graviton is not strongly bound, which means that the force is dissipated, right? So you get a weak force as a result of that. So gravity can move freely, right? Gravitons, right? Gravitons. This is what we're talking about. The gravitons can move freely through the brain, right? So that's what leads to this weaker interactive force. So that's a pretty cool thing, right? That they now have an explanation. So up until now, we just said, well, we observed that gravity is weak. But now they're saying they're actually giving us a reason, a rationale for why gravity is so weak. Okay, so now I do want to tell you that there is actually a new version of string theory, or you might have heard about it actually, and I want to bring it up to you. It's the concept of supersymmetry, supersymmetric string theory. I want to make sure you're aware of this. So what is supersymmetric string theory? Actually, you know what? Let's go. I don't know the correct definition. I just have an idea. I think I understand what it's about. But let's just see if I can look that up. Oh, I forgot to ask you guys. We'll come back to that. Supersymmetric. Actually, you know what? I should talk about it before I do this. Anybody remember the name of the theory that Ed Witten came up with? I forgot. It's called M theory, right? I forgot to tell you about that. Okay, so I should make sure that we talk about that real quick, because I don't know if I'm right about this. But anyways, in the movie, it's called M theory. And what does the M stand for?
Magic, mystery, matrix, or murky.
Right. Okay. So he actually attributed. I don't know why I chose just one, but I think I made one answer correct. But you're right. It's like
you said it's the one that he said he probably shouldn't have said out loud.
Yeah. So that's the one. That's the one that I used, right? So I think I used murky, right? I said murky. But really, there are, multiple versions of what the M might stand for. The M is not meant to be a particular word necessarily. And in fact, the murky indicates how difficult it is to understand anything. It's magical because of this ability to explain everything. It's kind of it's M theory. But the M theory idea is a unifying structure in which all of these 5 different theories now fit. It has 11 dimensions. Okay, that's one of the requirements to do that unification. But the question is, what is supersymmetric string theory? How is it different? And or what's changed? Okay, so supersymmetric string theory. Let's see. Hold on. I'm gonna. Let me just go ahead and take you guys to the Wikipedia page where I'm at. Okay, so this is. There's some fun words in here, by the way. There's some really neat things. And actually, I would love for you. Superstring theory is a shorthand, or superstring theory. Okay. Since the second superstring revolution, the 5 superstring theories are regarded as different. Oh, so I might be wrong. Okay, so this is, do you see this? This is a picture trying to illustrate a really complicated structure, right? It's the brain, or a bunch of strings connected together, a D brain they call it. But there's actually mathematics to describe these surfaces. Okay, and the name is really cool. I don't see the name here though. Maybe under mathematics. Monstrous moonshine. Mirror symmetry. Oh, here we go. Calabi-Yau manifolds. That's the name. Write that name down. Calabi-Yau manifolds. That's the name for that mathematical structure that you see. And so if you want to learn more about this, this is this is the mathematics to describe it. So in algebraic geometry and theoretical physics, mirror symmetry is a relationship between geometric objects called Calabi-Yau manifolds. The term refers to a situation where two manifolds look very different geometrically, but are nonetheless equivalent when compared mathematically. I don't know, whatever. Okay, so I do believe, maybe I'm a little confused about this. I thought that there were 11. Let's see. Superstring theory has developed blah, 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 lack of experiment, extra dimensions. Okay. So I understood that it wasn't 11 anymore. Oops, 10. Okay, hold on. Nothing prevented in 4 dimensions, blah, 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 to have 10 dimensions. Uh-oh, I said 11. Why is it 11? Extra dimensions
I'm
are
pretty
common.
sure the 11th dimension was introduced in M theory.
In M theory, yeah. Okay. Oh, and then here, it can be seen as a building on Kaluza-Klein theory, which is a 5-dimensional theory of blah, blah, blah. Okay, number of superstring theories. Okay. So M theory has 11 dimensions. Okay, but there are, I thought that supersymmetry had 22. Okay, I'm not seeing it. Now I'm not sure if that's right or wrong. I might be wrong about that. I thought that the supersymmetry needed 22. So I don't see it. I might be wrong. I might be wrong about that. Okay, so this is it. Yeah, M3 has 11. Chiral. I know what's tachyon. Oh my gosh, what's a tachyon? Right? Have you guys heard of that word before?
Yeah, this is the first time I've actually had the pleasure of learning about it.
Okay, so this is a tachyon. Write it down. Tachyon. What's a tachyon? We'll put that in your final. A tachyon. What's a tachyon? A hypothetical particle that always travels faster than light. So what's interesting about that? Let's read this. Let's read this. This could be funny. Tachyons travel faster than light, and because of that, they have the ability to go back in time. So let's see, speed, go faster than the speed of light. Time, causality. Okay, causality is the fundamental principle of physics. If tachyons can transmit information faster than light, then according to relativity, they violate causality, leading to logical paradoxes. This is often illustrated with the tachyon telephone paradox. Oh, I've never heard of that. Should we look that up? I would like to know that. Would you guys like to hear about this?
That sounds kind of cool.
Yeah,
Yep.
okay. Okay, so let's read this. Tachyon telephone paradox. The tachyonic anti-telephone is a hypothetical device that could be used to send signals into one's own past. So Einstein presented a thought experiment of how faster than light signals can lead to a paradox of causality, which would be a telegraph to the past. Okay. It's also called Tolman's paradox. No such blah, 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 blah. One-way example. Okay. But we haven't done too much of the diagram, so. Okay, so I think this is a problem right here, right? This is your gamma doesn't make sense if your v is faster than c. Okay, so, okay, I don't know. Yeah, so we've got a problem. So tachyons, I guess you would write down if there's a tachyon that allows you to it goes faster than the speed of light, it would allow you to go back in time. I don't think that's, I'm not sure if that's going to be real, but would be interesting, wouldn't it? Okay, and I don't see 22 dimensions. Why do I think there's 22 dimensions? 22 dimensions. String theory. Okay, why do I think there's 22 dimensions? Bosonic string theory. 26 dimensions. Huh, I think I had that wrong. Okay, so bosonic theory is the original version of string theory developed in the late 1960s. It is so called because it only contains bosons. In the 1980s, supersymmetry was discovered in the context of string theory, and a new version of string theory called superstring theory, supersymmetric string theory, became the real focus. So I think I've been wrong about the 22, and I don't know why I didn't notice that. See, the bosonic theories in a space-time of 26 dimensions. Oh, maybe that's it, 22 excess dimensions. Yeah, maybe that's what I got confused by. Anyways, let's forget about that. Let's forget about that. We don't have to worry about that. Okay, so anyways, so we have M theory. We have these cool pictures of Calabi-Yau manifolds. And then what else? So the current state of affairs is that there is no experiment that has been performed yet to prove string theory. It doesn't mean it's not going to happen. It hasn't happened yet. So, you know, this is one of the reasons why people are a little bit insecure about it. They don't actually know if we're going to be able to prove string theory at some point in the future. So I do want to share with you something that I just learned recently, and I think I might have told you a little bit about this. String theory can produce Einstein's field equations, right? You can get them. And actually, what's amazing is that they have managed to create Einstein's field equations using string theory. So that's great, right? Einstein's field equations. And so general relativity, you look at the field equations. We've looked at it, it's been a while, but let's look again. General relativity, bring you back here to remind you. This is something we've looked at again. Let's take a look. So here is the equation right here. G mu nu plus lambda, so big G mu nu plus lambda little g mu nu equals 8 pi g over c to the fourth t capital T mu nu. Okay, so this is the field equation, and string theory has made it, right? So you're like, wow, that's perfect, right? And I was pretty excited to hear this, but the string theorist who told us actually came out and said, except there's a little problem, right? Every version that they've created that actually fits into this equation and seems to work perfectly has a lambda, which is negative. And so we have a problem, right? It's exactly the opposite of what we see in our universe. And so somehow these string theories, although they can be fit into the field equation, and so remember how this works again. This is the what is this? This is called the what is this G? We have stress energy and the curvature tensor, the curvature, scalar curvature. Okay, oh yeah, that's curvature tensor. Okay, the big G is the curvature tensor, the curvature of space-time. And this is a lambda, this is called, lambda's the cosmological constant. G mu nu is called the scalar curvature, which is a little bit different. And then this is a big constant. This is our gravitational constant from Newton, and this is c, speed of light. And then T mu nu is the stress energy tensor. So, or this is the energy and mass that is causing the curvature of space-time, right? The energy or mass right here. This is the distribution of energy and mass. And here is the curvature it produces. And this is, again, something kind of associated. Remember, the lambda refers to the concept that there is a constant energy in space-time, even though it's expanding. And Einstein, you know, again, he took that out when he thought it was wrong, and then we put it back in again because we see that the universe seems to be accelerating. And this is our dark energy. The lambda represents the repulsive force that we see expanding the universe. So the big problem, right, I just told you, is that even though it fits, right, so it fits, right, so G mu nu plus lambda, this is capital lambda, little g mu nu, sorry, equals, what was the rest, 8, is there an 8? 8 pi? 8 pi g, 8 pi big G over c to the 4th, and then t mu nu. Okay, so this is the equation that they can produce, but unfortunately, the string theory only produces lambda, which is negative, right? And what would that mean, right? It would be a contracting universe. Right? It would not be the expanding universe that we see. So that's wrong because we see an expanding universe. So it's cool that it works, and that's actually giving people hope, except it's giving us the wrong answer, in which case it's not very useful, is it? So one of the ideas is that string theory is just too big. The string theory is too big. Right? That what it does is describes the possibilities of every possible universe, right? Every possible universe. And we don't live in every possible universe, we live in our little universe. So the concept is that even though string theory might be the right way to describe the universe, the problem is that it's just so big, right? Our universe is just one of the tiny possibilities that are there within the string theory. So imagine the space, right, of possible mathematical solutions for the universe, right? And then, you know, this is what it expresses, right? All of these possibilities, except ours is just this little one right here. So it's there, it's within string theory, but it's not dominant, right? It's not the one thing that we end up coming up with. We end up coming up with every possible combination, every possible solution to how the forces and you know, the interactions and the particles must exist. And so it's just too many possibilities. So, you know, how do they hone in? How do they get to here? How do they find our universe, which is just one tiny little corner of the possibilities, right? And the answer is, I don't know. They need some guides, right? They need something that gets them to this region where what they predict is actually reflected in our reality. So it's not, I have a good deal of, I'm excited about string theory. I don't know if I have faith. I'm excited about it. I think that they are making progress, and you know, they're certainly doing some really fancy math, and if nothing else, it's impressive, and we're gaining knowledge on the mathematical frontier. But I really do hope, you know, that it comes to some fruition, right? That it actually is able to one day explain our universe. Okay, so I don't know. Anybody have comments? Anybody want to talk about something related to string theory? Something you thought about when we were talking today? I mean, there's just so much. Obviously, we can't talk about all of it, but what's your feeling? Do you like it? Not like it? Frustrated by it?
I'm definitely frustrated with our current lack of ideas for experiments to test it.
Yeah, so by the way, we don't have a lack of ideas, Lonnie, not at all.
Okay.
I mean, people are actively working on it. but they're really, it's confusing, right? Because nobody knows the answer. So, you know, you want to be able to say, well, the only thing we know is that we live in a universe that we can describe, and this string theory currently doesn't describe it very well. So yeah, it's frustrating, definitely. Okay, so, you know, I guess I'm glad you guys had a chance to watch the videos. You took a little quiz and blah, blah, blah. Let me just tell you guys about some other ideas that are out there. And we don't have time to really get into them, but there's a very interesting kind of competing idea for quantum gravity. And I don't understand it very well, but I want you to kind of at least hear the words from me. And I happen to know some people who've worked on it, and one of them is a faculty member here at Santa Barbara City College. Her name is Amy Thompson, Dr. Amy Thompson. Anybody know Dr. Amy Thompson? Dr. Amy Thompson? Thompson, I think it's a P, I forgot. Is there a P or no? Thompson, I think it's Thompson. But anyways, Dr. Amy Thompson, she got her PhD from UCSB. And it turns out that there is a theoretical group out at UCSB that is working on this area. We have another adjunct who's worked with us. He's not a doctor yet, but he's working on his PhD. His name is Joseph Swearingen. And he is not here at the moment. He's actually actively working on, so she is a faculty in physics faculty. Just so you guys know, if you ever want to like reach out to learn a little bit more about this, and you can't learn from me because I don't know that much. These are people. Joe is an adjunct. He'll probably come back. He wants to teach adjunct here. SBCC in physics and astronomy. Okay, and they worked on some really interesting. So she got her PhD. He's getting his PhD in a field called, it's part of quantum gravity. Let me say quantum gravity, but it's actually a little bit more. So a quantum theory of gravity, and I just want to get this right. I just want to say quantum loop gravity, but I don't know if that's the way they really talk about it. I think they do. Okay, loop quantum gravity. There we go. Loop quantum gravity. Now, immediately when you hear that, you might think that sounds a lot like the string theory, and that's the way I think. But apparently, they're not necessarily in agreement, and I don't know why exactly. So I just wanted to throw it out here. This is actually something that's pretty modern, right? But it would be, I believe, a competition to string theory. Competes with string theory as a candidate for quantum gravity. So what is loop quantum gravity? It's a theory of quantum gravity attempting to merge quantum mechanics. Isn't that kind of what string theory is doing too? All right, but anyways, let's find it out. Gravity is not a force, so it's not real. It's a property of space-time, but blah, blah, blah. Okay. Oh, okay, so I actually have an answer. I just realized something. I actually do know something about this. Okay, so what's the difference between string theory and loop quantum gravity? So I want to write this down for you because I just read an article about this to help me understand this. String theory assumes space and time. I'm just going to write that down. Okay, what does it mean to assume it? That these exist already, right? I could write the word exist, but I just mean these are assumptions, right? There is space and there is time. Let's build a theory. Does that make sense? And the loop quantum gravity says, you're going to like this, space and time are condensates of quantum foam. Okay, so space and time do not exist. Quantum foam exists, although what is that, right? But this space and time condense out of the quantum foam and create the reality that you and I are in, right? But that they come from this generic quantum foam, right? Which I find this is kind of an interesting thing. So they have a name. They're called spin networks, spin foam. Okay, so quantum foam. The real name is spin networks or spin foam. Okay, that's the name for this quantum foam. And it's, again, actually on the scale, the quantum foam is on the scale of the Planck length, 10 to the negative 35th meters, right? This is the same concept of string theory, right? So you've got to start with something that's the scale of the smallest possible thing, the Planck scale, and then build it up to something that we recognize, right? So the loop quantum gravity, are you guys seeing this? You're still seeing this, okay. So this is the spin foam playing, blah, 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 okay. The most well-developed theory, okay, is loop quantum cosmology. The loop quantum cosmology advances the study of the early universe, incorporating the concept of the Big Bang into the broader theory of the Big Bounce, which envisions the Big Bang as a period of expansion that will be followed by a period of contraction, which is maybe the big crunch. So blah, 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 blah. There's a lot of stuff here. It's too many words, but oh my gosh, this is too much. Okay, well, I just wanted to mention these are competing. And you see, that's actually, I think I wrote down the major difference then. I actually think I already wrote down the major difference is the assumptions, okay? So assuming that space and time exists, string theory builds off of, space and time already existing. In the loop quantum gravity, they're trying to create space and time from some generic foam, right? And then, so space and time themselves, it seems to me like they maybe not be, I don't know why they're competing, because it feels like string theory is something almost similar, right? I mean, they say let's have space and time, but don't they build manifolds, the brains, to create space and time? And so again, even though you're assuming it exists, you're building it. I don't know. I'm not sure. I don't know. I'm not sure what to tell you. Okay, so I'm pretty much done with string theory for now. I do want to let you know about your work for Wednesday. And also, let's see, what am I going to do? I guess I will give you like a brief I'll write a participation quiz for you so that you can prove that you were here and you watched the lecture and listened to some of the ideas, maybe had some of the ideas of your own. But let's go ahead and take a look at what you have to do for Wednesday. On Wednesday, we're going to talk a little bit about gravitational waves. Okay, and it's pretty exciting. Actually, it's more exciting than I have time to talk about everything. So let's see what I put here. I put okay. So actually, I should show you this. Let's see. Okay. So we will finish right now. Just 1 second. Share screen. Okay. So if you go to your Canvas. I do want to let you guys know, I forgot to tell you this, that we have a guest speaker coming on Friday, Jared Goldberg. Some of you might know him. He is actually going to give us a talk on stars exploding. He's getting his PhD in astrophysics, and he will talk about what kind of stars explode and how do they explode. But he's also going to have time for question and answer. So he is getting his PhD right now. And it's kind of a fun thing. You can hear from somebody getting their PhD, what are they going through? And, again, if you have questions during the talk or you have questions before the talk, bring them in and we'll have time at the end of the talk to ask them. That's on Friday at 1 p.m. So the problem is we're going to do Zoom just for a couple of people, and then we're going to stream it. And we're going to have, so the president of the Astronomy Club will be moderating the questions from YouTube, and then we'll be asking Jared to answer those. So I would encourage you to come. That's on Friday, 1 p.m. will be the live stream. And then I don't see my assignment. Where is my assignment? Oh, I don't see it. Where did it go? Oh, no, I don't see it. Okay, so I messed up. I put this thing, but I don't want you to see that yet. Let's see, hold on. I don't know why, because I didn't give it a due date. That's why. Okay, so we're going to talk about gravitational waves. Oh, I didn't publish it. That's why. Okay, so I'm going to ask you to click on this. I'll publish it right now. To go to the LIGO website. So let's go there, take a look. Can you guys see the LIGO website? I'm going to see if you guys can see it. Yeah, it looks like you guys are looking at it, right? And you can look through here. This is a really cool thing, and there's other things. There's a gallery. This is actually way too much stuff. I don't really want you to spend more than a little while, but the educational stuff right here, learn more, right? Learn about gravitational waves and how they're detected. Okay, and that's one of the assignments, one of the things to do. And then here, this is important. This is your first, I don't know why I waited so long, but this is the physical review letter, which announced, can you guys see this? Oh, you can already see it, okay. This is a big thing. I mean, January 2016, observation. I can't even tell you how exciting this was. And you're just a couple years after the fact, but this is the first detected gravitational wave. And they describe, you know, what happened. But then you go down here, blah, blah, blah. This is the distance to it. And there's a redshift thing, and I need to talk about that because I never did. And the two black holes are 36, +5 or -4, or 29, +4, -4, plus or minus 4. So this is a range of possible masses, right? From 32, that's -4, up to 41, and a range of possible masses for the other black hole from 25 to 33. And when they combine, so looking at the best numbers, you get something with 62, right? 36 and 29 make 65, but you get 62 with 3 masses radiated in gravitational waves. Okay, this is delicious. This is amazing. So just look it over. I don't expect you to understand so much, but just look at it. And the main result is expressed right here. Okay, this is the main result. Okay, so, and then last part is, this is super exciting. Oh, I forgot to put it in here. That's what I forgot to do. Okay, and there's a page here on Wikipedia, which is really cool, but again, way too much information. And then the last thing, you please do this, is I have put up here an assignment to watch a little video. Where is it? Okay, it's under quizzes, so it's the first kilonova. Okay, and there's a short little quiz. It's a 5-minute video, 5 minutes video, and then here is another video. I don't know why I have this. Oh, but it's pretty cool. Okay, so I've got like 10 minutes worth of video to watch and then take a little quiz. Okay, and so that is it for today. Thank you guys very much. Anybody have questions? Otherwise, we'll complete our course for today. But come Wednesday, having read about gravitational waves. All right, so thank you guys very much. Have a good day.
Thank you. Have a good day.
You too. Okay. All right. I'll see you guys later. See you on Wednesday.
Yep. See you Wednesday, Professor. Thank you very much.
Bye.